Welcome back to Google DeepMind, the podcast, with me, your host, Professor Hannah Fry. I think it's fair to say that generative AI, as we have it now, is a bit of a mismatch for our science fiction fantasies about what technology might become. But it is worth remembering that this isn't the only possibility. There are other forms of AI, forms which are by their very design autonomous entities. These AI are firmly in the realm of robot butlers or a virtual concierge that anticipates your every whim before you even have it. And okay, we might have to wait a little while for those two particular examples, but I'm talking here about artificial intelligence with agency. AI that has built-in wants and objectives and the ability to independently make decision after decision in pursuit of its own goals. This kind of AI are known as agents. And while agents haven't yet exploded into the public consciousness quite as much as generative AI has, trust us, they are going to be a very big deal. And in the meantime, a very good training ground for agents is the world of video games. Think about it. Perfectly packaged, neatly constrained environments where the agents can run wild, work out the rules for themselves, and learn how to handle autonomy. If you've been following us since the beginning, then you will know that AI and games is something that DeepMind has a proud heritage in. And so to explain today, we are joined by Frederic Besse, who's a senior staff research engineer at Google DeepMind. Frederic has a PhD in computer vision and was one of the earliest people to join the DeepMind team back in 2015, when there were only about 100 researchers here. And before the decade he spent at the cutting edge of artificial intelligence, he also spent some time working in the visual effects industry on how to integrate CGI into real footage. Frederic, thank you so much for joining us. With a CV like that, I can see why they wanted you.
Oh, well, thanks.
Okay, well, so I think it's probably best if we start off with some definitions.
Sure.
So, I mean, I talked briefly about what agents are there, but how do you define them?
So, in my mind, an agent is a very general concept, and I define it as an entity that can act in an environment. I think action is what defines an agent. And an environment, on the other side, is a place which can provide observations for the agent and which the agent can interact with. And so what's important to understand is that the agent, by acting into the environment, will change the environment, which is crucial for developing AI systems that can do useful things and understand the consequences of their actions in environments, in games, in the world, on the internet, etc.
This sounds like something that exists beyond just AI, though. I mean, like autopilot on planes, would that count as an agent?
Yes, absolutely. So maybe we can give a few examples of agents, because it's a very general concept. So humans are agents because we can act. We observe the world with our eyes and our ears. We have proprioception. We know where our limbs are. So we are agents. We can affect the world. Similarly, robots as well. But if you go back to maybe decades ago, where we had agents such as autopilot, which we handcrafted the logic of those agents. We were programming them to do what we wanted them to do. So they were different from the modern agents that we can talk about later on, but these were indeed examples of agents.
So, all right, if that's an agent, then is that the same thing as autonomy or having agency? Are these all slightly subtly different?
So I think they are subtly different. I think an agent can act and do things that it has been programmed to do. And that's agency, being able to take actions. Now, autonomy is more the skill or the property of acting by itself to accomplish a certain task. And there are various levels of autonomy. So if we have a self-driving car, which will take decision to best navigate the roads, you could say that there is a certain level of autonomy. Some agents are much less autonomous and will require a lot more of your input. And then on the other end of the spectrum, you could have an agent that goes in the world and learn new things, explore, which we don't really have to instruct much. So there are a spectrum in the space of autonomy.
Is part of that like almost a hierarchy of the type of objectives that you're setting? Like, I don't know, the autonomous action of like picking up a cup and putting it down is slightly different to deciding what's for lunch.
Yes, because we are training agents to do simple things, because this is a starting point. But having an agent that can cook for you your whole lunch will
decide what you want as well would be nice.
Yes, as well, it could be a recommender system. Will require a lot of sub-steps and sub-tasks and solve those tasks properly as well first. So we call those high-level tasks compared to short horizon tasks, which will be very basic, almost mechanical actions, like grab an object, put the object on the table, compared to cook lunch.
Yeah, like the robots you see in factories, for example, versus the type of ones that we have in science fiction. But is that the sort of aim? Are we talking about robots eventually that will be in our homes?
I think so. So what we are trying to do is to develop general agents, and we want to reach a point which we call AGI, Artificial General Intelligence, which is a point where we will have agents and AI systems that will be truly general as humans. We'll be able to adapt to new situations, reason like we do, and even surpass our capabilities in doing tasks. Once we reach this level of competency in AI systems, this will unlock a lot of potential for what we can do as humans. Those AI systems will be able to accelerate our scientific progress, for example, or do a lot of tasks which maybe we are not very good for. For example, maybe driving, or help you in your home, help you do shopping online. I think there are some applications which we can't even begin to conceive, because this is such a technological leap that I think we will just discover it as we go. But we do believe that building such general agents, which can act into an environment, is key to achieve AGI.
That's interesting then, the way that you're describing it, that some of these agents are going to be virtual, essentially,
yes,
and then some of them will be actually physically embedded in an environment.
Yes, so I think it all goes back to what's your observation space and what's your action space. So we can have physical agents, embodied physical agents like robots, which will be able to do things in the real world, which will be very useful. And we already, as you...
My robot butler, thank you. Yes.
Exactly. But also virtual agents which work not in the real world, but in an abstract virtual space. This could be still a physical space, for example, games, which we use in our research to also demonstrate and understand what those agents can do. But also you could have an agent that doesn't have any physical, even virtual action space, but instead it can make programs, for example, write Python code, build software for you, which is not a physical space, but it's still an agent because it can take actions, it can compile the function, it can look on the internet, and so this is still very valuable.
How is this different to the chatbots that we've seen from large language models? Because, they can do a lot of that stuff too, right? They can search the internet, they can understand your instructions and make decisions, sort of?
Yeah, so chatbots, what you get out of chatbots generally is a chat output. So they produce natural language. Now, there are some capabilities in some chatbots which could go and search the internet for you. But this space is still fairly constrained to just being either natural language or specific functions that the programmer adds to the chatbot to do things. Now, those chatbots, when they speak with you, in a way, you are the environment of the chatbot, right? What the chatbot says will affect you and will affect what you ask the chatbot next. But maybe it's not as, there is not as much consequence as if the chatbot or the agent was acting in an environment which drastically changes when the agent takes some action. So it's a bit more of a passive type of agent. We could call it an agent, but it's very different from an agent that act in the real world. And the way also those models are trained, they are trained with a lot of data that is scraped from the internet, but they are not trained in an environment to try to do things, fail, understand why they failed, and try again. So this is the difference between some of the way those models are trained with human data.
So then, Should we be thinking of these as separate, or can you combine the two? Can you combine large language models and an agent that has an objective?
So you can, and actually there are some robotics paper from Google DeepMind that's it's called RT2 and RTX, which are doing that. So they are training. So a language model has a lot of knowledge from the internet scale data that it's been trained on. So if you want, it has a lot of common sense and it understands a bunch of concepts, but it doesn't have the ability to actuate joints of a robot. But you can take this model and train it to produce joint activation for your robotic arm, for example. That's what they've done in that paper.
I guess almost the language model gives the algorithm some sort of, inverted commas, conceptual understanding of things.
Yes. I think that's what is great about those big models, is that they have such knowledge and understand concepts and words and what you chat to them about, that they can make plans. But all of this is in language space, right? And we need to bridge the gap towards acting in the real world or in the virtual world.
To go off and actually enact it.
Yes.
What is it about games, though? Why is it useful to start with games?
So I think games offer a very rich experience, and games are very varied. So if you look at how many games there are on computers, for example, you have tens of thousands of games, and each game offers you different scenarios, different environments, different things you could be doing in the game. So we think it's a great proving ground to train AI systems to match human performance. There are other advantages in games. So they are virtual, so they are easy to scale. You could instantiate a lot of different games in parallel, compared to physical systems, which are constraints to the real world. They are also safe. So if things go wrong in games, it doesn't really matter. It's just a game. Games are a place where humans can interact with agents, for example, in multiplayer games. And games are, fun as well for humans to play. And I think it's a great source of experience data that we can collect.
I guess you've already got agents already in sort of non-player characters, right? NPCs floating around the place.
Yes. So I think that's a very interesting point. Historically, and actually it's still the case, when game developers create agents inside of games, it's a very different beast to the type of agents that we make. Those agents have access to the internal code of the game, and the game developers just write the logic, which works great, and they are fast, and they can do pretty impressive things.
Things like stand around, and then if someone approaches you, attack them. I mean, that's
I mean, there is some pretty complicated logic you could put in the game, in the agents in the game, in the NPCs. But there is like a limit in how complicated you can describe behavior in terms of code, and that's where deep learning and modern agents come in, because those are not, the logic inside those agents is not handcrafted by humans. Instead, we subject the agent to a lot of experience data, and the agent will learn the behavior for itself, and in a softer way, with more like nuances, and it can pick up on very complex behavior, which maybe wouldn't be feasible to write down in code, in programming language.
Rather than just following rules, it's sort of working out how to achieve its objective itself.
Yeah.
DeepMind's got quite a long history of playing around with games. Maybe that's a bit trivializes it slightly, considering the things that they've achieved by doing so.
Yes. So back in 2015, there was the first breakthrough in neural network agents called the DQN, for Deep Q Network, in which the agent was trained to play Atari. And the breakthrough here is that the agent was only using pixels as the observation space.
So Atari is like Space Invaders, Breakout, the one with the bricks where you've got a paddle and a ball bouncing around, like the sort of games you had in the 1980s.
Yes, so those arcade games. Yeah. Exactly.
And the only thing it would take as an input were the pixels on the screen.
So the pixels of the screen, and there was also the concept of reward, which is like how many points you get. And that is very important for those agents to learn, because what those agents are doing and how they are trained using a method called reinforcement learning, which aims at maximizing this score, maximizing the reward. And so combining deep learning with deep neural network and reinforcement learning yielded the DQN agent, which was first of its kind. And that was a very big milestone for DeepMind. Then another important agent that was built was AlphaGo, which was an agent that tries to learn to play the game of Go, which is a board game.
Notoriously difficult.
Notoriously difficult. I think it was uncertain whether AI could ever beat the game of Go, but then that was proven to be wrong.
When AlphaGo beat Lee Sedol.
Yes, exactly. So that was a huge result. Then if you continue along the history, so this is a non-exhaustive list because there is a lot of research that has been happening also in between all these important milestones. There was AlphaZeo, which is taking the agents that play Go, and also it could play chess and shogi to the next level. And this agent was trained without any human data. So while AlphaGo was trained using a mix of human data and self-play and reinforcement learning, AlphaZeo was trained without any human data. And just starting from scratch with self-play, it discovered the best chess moves. And that was very interesting to see.
Extraordinary that taking the human input out made it better.
Well, yes. So it's interesting because you can actually look at what are the most optimal moves for chess, which is fascinating, I find.
But then it moved into computer games again, didn't it?
Yes. So I think one next very important paper was the AlphaStar paper, which is an agent that is playing StarCraft 2, which is a game, competitive game. That's very different environment from, say, Go or chess, right? So one of the challenge here is that in StarCraft 2, you only see partial information from your environment. There is this thing called fog of war, where you cannot see what your enemy is doing. And so you really have to take this into account during your kind of strategy. While in Go, in chess, you see the whole board in front of you. So you have access to the whole state of the game. Also, the agent has to play in real time because StarCraft 2, once you play against a human at this time, you really have to play as fast as you can so that you cannot take minutes to think. And the StarCraft 2 agent was able to beat very, very good humans at the game.
So now this is one step on even further. So it's like at every step you remove something that made it easy. So Atari, you get points for every action. Chess, you don't. In chess, you get to see the entire board. In StarCraft, you don't. Yes. In StarCraft, it's competitive. In what you're doing now, it isn't.
Yes. So those agents were trying to maximize the score and to win the game. While what we do in SIMA is very different. We train agents to follow instructions.
What's this project called?
Our project is called SIMA. That stands for Scalable Instructable Multiworld Agent. And we used various different video games and also research environments to train an agent to follow instructions that we ask it to do. Those instructions are fairly simple, that you can typically carry out in 5 to 10 seconds, such as pick up the apple or turn around, climb up the ladder, etc. And so there is no score, and we use the games really as containers, as walls, in which we can carry out a whole bunch of instructions. And the amount of instruction, the number of instructions that you can come up with is very large due to the fact that we use natural language to formulate those instructions. So this poses other challenges. We really want to make our agents to be general. So while a Go agent only learns to beat the game of Go, we are interested in making an agent that can really understand what you're saying, understand the context, understand the environment, and then carry out this instruction. And so we are aiming for generality. And I think generality is a key property that we want in our agents to pursue AGI.
What do you mean by sandbox games?
So a sandbox game is a game where the player can basically do whatever they want within the space of what the game offers. So if it's a game which has a natural landscape, you can craft, you can build, you can cook, you can explore.
Like Minecraft,
like Minecraft. That's what we call a sandbox game, because there is not really like a goal to the game. Mm-hmm. Some games are sandbox with a goal. So it's a bit of a mix. But you just have fun and do a bunch of things.
Like in an actual sandbox.
Exactly, yes.
Well, how about you? Are you a gamer?
Yes, very much so. I was given a Game Boy for my 6th birthday.
6th birthday, amazing.
Yes,
Lucky thing.
Yeah, it was amazing. I think my first game was Tetris, and yeah, I was amazed by being able to play those games in the car. The car trips were never the same after that.
Yeah, it's true. And as an adult, did you go beyond Tetris?
Yes, of course. I remember when we at home got a DSL, which could give you basically constant internet access. I was very happy because I could finally play online games without being worried about the counter. How much time do I spend on the internet? So yeah, online games, competitive games, Sandbox games, and survival games. All of this, yeah, I do quite like.
I mean, so you've got basically the perfect experience then to be in this space.
Looks like it.
The new projects that you're working on now, these Sandbox games, I mean, they are quite a big departure. How hard is it to get an agent to achieve things in an environment where you don't have that really clearly defined metric of success? Yeah,
so it is a very different style of building an agent training from before. There is some prior work which we were very inspired by, which was the Interactive Agents project. There is a blog post on the DeepMind blog post where they used a playhouse environment with a bunch of objects, and the goal was to get the agent to carry out instructions in that house.
It's like a simulated environment.
It's a simulated environment, yes. It's like a children's house with colorful objects, and the goal was take the teapots and put it on the bed, and there was no reward as well. So we wanted to take this to the next level, and we also wanted to use games that are not games that we make ourselves, that are available for everyone to play.
So basically, it's the games that you guys play. Is that what it is?
Some of them are indeed.
I just want more time to spend on this game that I've been doing, so I'm going to build an agent to do it. That's essentially what it sounds like.
Yeah, you could, yeah. And so, yeah, we got into partnership with game developers and game studios to be able to use their games in our research. And we picked games which are of a certain genre. So we wanted 3D games because we were interested in this embodied 3D setup. We wanted to be able to define our own objective with language. So if you go into Valheim, for example, which is a Viking survival simulation, you can make up a lot of tasks for the agent. You can say, go get some wood, build a house, craft a jacket, etc.
Then how on earth do you train an agent when you don't have rewards?
So what we did is that we collected data from humans playing the game. And then we used a technique called limitation learning, which teaches the agent to just mimic and predict what a human would do next. So given all of this observation, given what you've done before, what would a human do? And that's how we train the behavior of the agent. So there is no reward. We just imitate humans,
Is it probabilistic then? Is it sort of like, in this sort of situation, humans acted in this way, so we'll act in that way with this probability?
Yes, exactly. So all the actions of the agent are probabilistic. So before the agent acts, there is a probability distribution which needs to sample and pick an action from. Often it's the most likely action, but sometimes you can take an unlikely action which can lead to unforeseen behavior. Sometimes it's a good behavior. Sometimes it's not.
Go on, give me an example.
Well, so for example, we have games such as Goat Simulator.
Tell us the objective of Goat Simulator.
So the objective of Goat Simulator is to basically cause mayhem as a goat in a world, and you can drive cars, you can jump on objects
as a goat.
Yeah, you're a goat. You can have wings and you can fly as well. But it's a perfect sandbox game because you can do so many different things. And so in Goat Simulator, there is a key which causes the goat to become all floppy and ragdoll on the floor. I'm not too sure what's the... when you would actually, as a player, use this, maybe to pretend out.
Play dead.
Exactly. But sometimes when we play test the agents, it ragdolls on the floor, which brings some funny moments in the team when we do the playtest.
Just expecting it to barge into a crowd of people and it just ragdolls.
Yes, that can happen.
Can I see what it looks like?
Yeah, I'll show you. So
go on.
Here, let's start by Goat Simulator 3.
My fave.
So we have a video of the agent here, which the instruction is to go to a green object.
shortcuts. Okay, we've got a goat. We've got a quite realistic environment. And we've got the goat trotting forwards. There's plenty of green, which the goat is walking past, but it's doing a big jump into a pond. And in the pond, there is an inflatable in the shape of a snake, which the goat has successfully reached.
It's green.
It's
Yes.
definitely green.
So we count
and
it
it
as
is
a
an
success.
object.
It's an object, yes.
And it did a jump there to get there.
Yeah. So sometimes the agent pick up on some human peculiarities. For example, humans, when they play games, are often bored to take the longest path. For example, climbing up the stairs. If you have a jetpack, you're just going to jetpack over the stairs. So one of the first agents where we asked get up to the platform, instead of taking the stairs the long way, the agent just jetpacked over the stairs. So it does learn about human behavior.
The strange shortcuts. I also noticed that rather than just walking into the pond, it jumped, which is exactly what I would do as a human.
Yeah.
You want to make a splash.
Yes.
Okay. All right. Well, I mean, it succeeded.
Yeah. So this is the game Valheim, which is a Viking survival sandbox game. And the task here that we ask the agent to carry out is to pick up mushrooms.
Okay. So again, another very beautifully crafted environment. The camera is moving around, which I guess is the agent doing that, moving the camera around. It has found quite quickly some mushrooms, shot them out of the ground. I don't know whether the Vikings had that particular ability. And just carrying on wandering through the forest.
Yeah.
Okay, so definitely like camera control and movement in that 3D environment, it's mastered.
Yes, so I think because all the games that we use are 3D games, the camera control is very similar from all those games. So I think there is a lot of experience to learn from in terms of controlling the camera. You can see that the movement of the camera is human-like, so it hesitates. It's not very robotic, like just aim on the mushroom and go forward. And that's because it's trained from human data. If you train an agent with reinforcement learning to do the same task, if you could detect
as opposed
success,
to imitation learning.
As opposed to imitation learning, the agent would have very linear and robotic camera motion. It would just go to the mushroom because it needs to optimize its reward. So it will not spend any time hesitating.
When you're instructing the agent, you're not explaining what a mushroom is or what a mushroom might look like in the game.
Yeah, so it gets that from the training data. So in this training data, there is a bunch of sequences of humans interacting with mushrooms, picking up mushrooms, and so it just learns from the data. So an interesting task we could ask the agent here is, if you hold out, if the agent has never seen mushrooms, or maybe never seen red mushrooms, but maybe it has seen blue mushrooms, and you ask the agent pick up the red mushrooms, is the agent able to generalize, color and object type?
Yeah.
So those type of questions are the questions we are interested in.
Which is definitely demonstrating a sort of conceptual understanding of the environment that it's in.
Yeah, it would, yes. We're looking for this generality and transfer between concepts and trying to put things together, new concepts together to carry out a task. And this will show understanding of what a mushroom is and what the color red is.
In a way, the way that you describe the imitation part of it, the imitation learning, it sounds a little bit like you're doing a sort of computer game version of predictive text, almost. Like what has been done in this environment before, how do you repeat it?
It is exactly that. So,
is it?
So yes. So when you train language models on language, the objective in which you train, at least the initial model, is to predict what's the next token. So what would, if it's assuming that it's all human-generated text, what would a human say next? What word would a human say next? Which is very similar to this, which is what would a human do next in terms of the keyboard and mouse action. So you're right, it is pretty much the same technique.
The same ideas. Mm-hmm. But the key difference here is that you're instructing it. You're saying, this is the objective for you, and go and do that in a way that a human would do.
Yeah, so it's given this instruction, what would a human do next?
Got
but
you.
The language models are also, in a way, prompted with some prior text. So they will say, given that this text is in your prompt, what is the next most probable word that you should output? So it's not very different. The maybe infrastructure and architecture of the agent itself is a bit different because we here need to produce a very different modality, which is action in keyboard and mouse space.
It sounds like it's kind of exploring the network of actions that people have taken in the past. does it do original things then?
So it will not do anything that humans haven't done per se, but the agent is able to generalize to unseen environments. So in a way, that's kind of novel. So it's like, I don't know, you're a tennis player, and suddenly you're asked to do a badminton match, right, as a human. Because you've learned tennis, you have some reflexes and mechanics that you know how to hold a racket, you know how to strike a ball. And so you're going to do fairly well at badminton. Not the best, but you're not going to be beginner level. And in our agent, we see the same. So what we've done is that we train the agent on all the environments except one, and then we test the agent on that one environment. And we can see that the agent is able to do a few things at a reasonable level in that environment. So in a way, I don't know if you can say those are novel, but it definitely shows some promise with respect to generalization and generalizing to unseen environments.
So, okay, tell me how well does it perform overall then?
Maybe I can tell you about two interesting results.
Yes, please.
So first of all, we observe that when we train an agent on all of the environment, it performs better than an agent that is only trained on each singular individual environment.
So you train an agent on No Man's Sky, Goat Simulator 3, Valhalla.
Yes.
And then it does better in, for example, Goat Simulator 3 than an agent that is trained only in Goat Simulator 3.
Exactly, yes. So that was a very good result for us because it demonstrates that the experience that you get from training on variety of game make your skill in each individual game stronger. So what I like to think of is, let's say, as a human, maybe I to go back to the tennis example, maybe I train on tennis and I train on badminton, and maybe I'll be better at both of those compared to if I had only trained on, say, tennis. Because maybe I gain some extra skills and subtlety in the type of actions I need to do from being exposed to a wider range of skills and experience.
Is it also partly they're just exposed to more data? So more of how humans manipulate 3D environments, more of, different kind of things that humans might do?
Yeah, so different games offer different situations. So the agent can extract knowledge from those situations and maybe relate them to other situations from other games. And so it just accumulates and consolidates the behavior into something that is better than not having seen this other experience, which in a way, our hypothesis when we started the project was the same hypothesis as the language models. Training on a lot of data will make some interesting properties emerge, such as being able to generalize and transfer. And so, that's what we also observed here.
But then I think also that result isn't immediately obvious, because it could well have been the case that actually all the things that it learns from No Man's Sky confuse it when it goes back to Goat Simulator 3.
Yes, so we were worried about that because we thought maybe there will be a destructive interference between games. That's true. We picked those games to all be 3D because we thought there was a chance that some of the experience would transfer between games. If we had trained on Tetris and No Man's Sky, we wouldn't expect any positive interference here.
Slightly different environment, isn't it?
Yes. But because all of those games have some similar concepts, same way of navigating around, moving the camera, we thought maybe there would be some interesting and positive outcome to training on multiple games.
You told me that there were two big results.
Yes. So the other result, which I mentioned before, was that when you train an agent on all environments but one, it performs roughly as well on this held out environment as the agent that has only been trained on that environment.
Okay, wait. So, you've got 8 games.
Yeah.
You train an agent on them and leave off Goat Simulator 3.
Yes.
It's never seen Goat Simulator 3 before. And then you sort of compare it against an agent that's seen nothing else but Goat Simulator 3.
Exactly.
And then you test them in Goat Simulator 3.
Yes. And the SIMA agent here performs nearly as well as the environment. We call it the environment expert because it's an expert in...
Yeah.
It's a GOAT expert.
Expert, sure.
So, yes, it doesn't perform as well on average, but it does perform reasonably well. So it has learned to generalize to unseen. All the other games have different avatars, for example. The agent has not.
There's no goats anywhere else. There's no goats in space.
But the agent is able to move the goat around and perform a few tasks. Of course, there are some actions in Goat Simulator which are specific and unique to Goat Simulator, and that we don't expect.
There's no ragdolling astronauts.
And we don't expect the agent to be able to get that because it has never seen it, or it has never seen experience from it. But other things like navigation, maybe concepts about objects and colors, that is something that it can achieve.
So how do you expand that beyond these sort of tasks that last for 10 seconds, 15 seconds of jumping in, picking up a mushroom?
We are working currently on trying to find ways of doing that. First of all, there is a lot to improve because our agent is not at human level, even for those short horizon tasks. For longer horizon tasks, we are looking into methods which would allow us to do that. You mentioned large language models before, which are able to maybe reason on a higher kind of time horizon, longer time horizon. So maybe combining those models with our agent could be a way. But that's future work.
Can I play alongside one of these things just to make my experience of the game better? Can I cheat, basically?
So some agents do find, ways of exploiting the games to do things that were not originally intended. So in a way, you could call that cheating, I guess. But playing, like once we have very competent AI systems which could do all sorts of things, playing games with you could also be one of the things you want to do with those systems. That would be quite fun, I think, especially in these sandbox games. If you had an agent which you could say, okay, now I want to play hide and seek in Goat Simulator. And let's say it's multiplayer, you have two goats and you can play whatever you want. I think it would be quite fun to interact with an agent in exactly the way you want. So the way we currently sometimes use large language models is we prompt them to do all sorts of things, write a poem, do some role play, write code. If we had the same ability, but also with an agent that has an avatar in-game, which you could prompt, I think that could be lots of fun for gamers.
Yeah, it's like level up on an NPC, isn't it?
Yeah.
Okay, so what is the big objective here then?
So I think what we are interested in the SIMA team is to build truly general agents. So we use games as a platform to drive innovation and breakthrough into this particular space so that we can get a step closer to AGI and understand how to build those truly general agents. So we are really in for the research towards AGI.
What's the definition of AGI that DeepMind worked to?
I think the definition of AGI is an agent that is as general and capable as a human. And I think the general is key here. Could be better than a human, but at least at human level.
So you can pick it up and drop it into different environments and it can do as well as a human can?
Yes. So I think if you think about gaming, right, as a human, maybe there is a new game coming out, I install it, and very quickly I will be able to play this game. Maybe I need to go through a tutorial because there are some specificity to the game that I need to learn. But in general, I think we are very good at adapting to those new situations, to those new environments, and be competent at it. And we really want the same for our agents. We want to drop the agent in a new environment or show it a new game and observe that they can indeed also adapt and become competent at those new situations.
Well, you've sort of done that already, haven't you?
There is still a long way to go. So our agents, have been trained to only perform simple actions, but really, there is so much more skills and scenarios which we could use to train our agents. How do we make an agent that could handle 1,000 different games? What does it take? There are some breakthrough that needs to happen.
So then let's say that you manage that, which I'm sure you will. What happens then? Is the idea that you can take that learning and then apply it to really generalist agents that exist in the environment that we all live in?
Yes, there are methods. How did we build the agent? I think the understanding what method we use to achieve this result is very important, so that we can then apply the same method to other domains which we might be interested in. Understanding technical kind of details of how to build those agents. Understanding how to collect the data, which data is useful, algorithms. How do we train the agent? I think that's very important as well. So yeah, any kind of innovation and progress we can make towards understanding the how to make progress in AGI is what we're after.
But these are lessons that can apply elsewhere.
They could apply to other domains, yes.
Okay, so give me an example then. What kind of agents should I be hoping for?
So are we talking about the far future now?
Yeah, go on.
Okay, so I think I could say example of agents would be self-driving cars that are safe and reliable. I think those are agents which take actions that have consequences, and so having very robust and reliable self-driving car which can generalize to unseen circumstances would be very important. And I think the generality here is very important, because when you drive, you never know what's going to happen. I mean, if we had agents in the real world, one obvious things we would like would be for agents to carry out instructions for us. For example, it would be or robot in your house, where you say, maybe carry this heavy object to the table. That's a task which is defined in language, which would be very useful. Maybe virtual agents which can code and write software would be very useful for us. Maybe agents that can help you in everyday tasks which you do online, for example, shopping. We spend a lot of time researching what to buy. If I want a new pair of headphones, I might spend hours to understand which one is good for me. But if I could have an agent that can do this research for me, that would be very useful, I think.
I'm just going back to your AGI stuff, actually, if I may, just to finish on. Do you think that the sparks of AGI will happen in your lab?
Well, that's very difficult to say, but we do hope, yes, that's the methods we develop will help to make progress towards AGI. I think if we had an agent that could play any games and carry out any instruction in any game,
and perform at superhuman ability.
And yes, I think that would be a good, a good milestone to achieve, because that would show human-level intelligence, at least in games. But games are very rich, and sometimes are a bit like the real world. You need to understand your surroundings, you need to understand objects, you need to understand the consequence of your actions, especially if you add language into the mix, because if you add language into the mix for tasks, then really you could ask the agent to do anything. So if such agent is able to carry out any instruction in any game, I think we would be, one step closer to AGI.
Fred, thank you very much for joining me.
Well, thank you so much for having me.
There have been a few moments now while making this podcast where we have been here at the early stages of a project, before the results were grand or headline grabbing, when there was only the tiniest little spark of something to see. Like, remember when we first visited the robot lab to watch them flailing around in circles? Or the first time that we saw AlphaFold, when it was only just starting to unravel the mysteries of proteins? Well, I think it feels a lot like this is the stage we're at with SIMA. Because sure, picking up a mushroom isn't quite the vision of the AI future that we've been waiting for, but it's the direction that those agents are moving in that really holds the secret promise to what might be possible. Because if we want AI that can make its own decisions, achieve its own objectives, operate independently of our instructions, then this is a vital step along the way. So today, it might be a mushroom. The question is, what will it be next time we come back? You've been listening to Google DeepMind, the podcast, with me, Professor Hannah Fry. If you like what you just heard, hit subscribe on YouTube or follow us on your favourite podcast platform. We've got an exciting lineup of conversations to come, including an interview with Pushmeet Kohli, who oversees science research at Google DeepMind. If you have someone in mind that you'd love to hear from on this podcast, do leave us a comment. See you next time.